Hi, my name is Stanley Osira, and I'll be presenting the tangent-based method for collision detection and avoidance for UAVs using an ADSB transponder and ADSB-like solution for the California State Polytechnic University, Pomona. As a general presentation overview, we'll be running up through our project objectives and motivations, the technical approach, our test vehicles, our concept of operations, our collision detection and avoidance algorithm, as well as the XB radio module, the hardware layout, data communication, and finally, our simulation and flight testing. In order for an unmanned aircraft to properly integrate into the national airspace system, an equivalent level of safety to manned aircraft must be established. This is facilitated by the ADSB sensor, a surveillance technology in which an aircraft determines its position via satellite navigation and periodically broadcasts it to nearby aircraft. Our system utilizes the XB radio module as an ADSB-like solution, as ADSB out functionality is prohibited on unmanned systems. Our technical approach is as follows. First, we integrate the radio module, in our case the XB, and flight controllers, in our case PIXOX, into our existing UAVs. Then, we develop our collision prediction and avoidance algorithms. We then proceed to test our algorithms extensively in both software-in-the-loop and hardware-in-the-loop simulations. This is followed by ground testing in order to ensure accurate data collection and, of course, facilitate troubleshooting. Finally, we experimentally validate our algorithms via extensive flight testing in different use case scenarios. Due to the limits placed on ADSB out functionality, our team surveyed a number of ADSB-like solutions. The XB radio module was the preferred solution, as it is lightweight, reliable, and has a low power consumption, all characteristics desirable for small unmanned vehicles. On the left, we have a modified Carbon Cub acting as our own ship, carrying an XB radio module, a PIXOC, and an onboard compute stick, enabling it to run our collision prediction and avoidance algorithms. On the right, we have a lightweight F450 frame. This is equipped with a GPS, a PIXOC cube, and an XB radio. This functions as our intruder vehicle, around which our own ship conducts its avoidance maneuvers. Here we have our concept of operations. Our fixed-wing aircraft begins the mission by taking flight, then proceeds to a waypoint mission. During the flight, our collision prediction algorithm predicts possible collision locations, altitudes, and velocities between both fixed-wing and intruder aircraft. Once a collision is predicted, we generate an avoidance waypoint based on situational characteristics. Then we proceed to maneuver to said waypoint. After we navigate to this waypoint, we then return to the navigation mission. Our procedure for collision avoidance is as follows. First, our function collision predicted compare detects possible collisions by comparing the future path of both vehicles. Then, we calculate an avoidance waypoint using the own ship and intruder X and Y positions. We then proceed towards the avoidance waypoint. Following this, we resume the mission after about 5 seconds. For our collision avoidance algorithm, we generate an ellipsoid surface centered on the intruder aircraft. This represents a safety region, so any point on the surface can't be reached by the intruder during own ship avoidance maneuvers. This surface is used to define the space where avoidance waypoints can be generated. Following the generation of the ellipsoid, we proceed to take a horizontal slice of the ellipsoid, corresponding to the desired energy state of the vehicle post-maneuver. We then generate 2 tangents to this elliptical slice, as well as 2 corresponding avoidance waypoints. We then select the closer point as our target avoidance waypoint. Here is a sample of our collision prediction code. We calculate our collision positions based on our tolerance region radii, our current positions, both vehicle velocities, and the amount of time taken in the future. If a collision is predicted, the own ship heads to an avoidance waypoint calculated by the avoid function shown to the right, using the own ship and intruder X and Y positions. Here is our sequence of operations. Our radio module continually sends and receives aircraft data, and our flight computer stores the pass-through data packets. Our telemetry communicates with Mission Planner, which sends waypoints. Finally, our flight computer constantly checks for future collisions in preparation for conflict resolution. Our conflict resolution functionality is described by the previous slides. Here we have our hardware layout. First, we have our Holy Bro telemetry, which enables communication between the PICSOC flight controller and the ground control station. Second, we have the AR7700 spectrum receiver, which enables communication with the operator on the ground, acting as the safety pilot. Third, we have the PICSOC Cube 2.1, which functions as our flight controller and gives us attitude data. Fourth, we have our GPS module, which gives us positional data. Fifth, we have the Intel Compute Stick, which runs both our collision avoidance and collision prediction algorithms. Finally, for number 6, we have our XB radio module, which functions as our ADSB equivalent. Here we have our hardware communication setup. The physical wire connections are shown in red. Data transmission in the air is shown in blue with arrows. On the left is the hardware on the fixed-wing UAV, and on the right is the hardware on the quadcopter. The fixed-wing UAV and quadcopter use the XB radio module to communicate their locations. The fixed-wing UAV also uses telemetry to communicate with the ground control station, so that the ground control station can monitor the fixed-wing UAV's status and missions. Here we show the communication between various components, including the communication between ground control station and the vehicles. The onboard computer processes the collision avoidance algorithm and intruder's flight data, such as the geographic coordinate and the velocities, and makes decisions and sends avoidance commands as Maverick messages to the PICSOC autopilot. The autopilot then commands the own ship to perform the specified collision avoidance maneuver. The onboard computer reads the GPS position of the controlled aircraft directly from the PICSOC through message packets using Mavlink protocol. The GPS locations of the intruder aircraft are received by the XB radio module and sent to the PICSOC autopilot, which then sends the data to the companion computer. After location data from both of the vehicles is stored, the companion computer starts calculating for a change of course maneuver using kinematic equations and a probability of collision. Once a collision is predicted, an avoidance maneuver is requested. The new avoidance waypoint will be calculated and sent to the PICSOC autopilot, which maneuvers the aircraft to a collision-free path. RGPilot Mission Planner includes software-in-the-loop simulation. This helps validate and debug the algorithm and simulation without using any hardware, so that any potential mishaps during flight testing can be avoided. The ability of the algorithm to add a waypoint that the own ship needs to travel to after performing collision avoidance maneuvers was tested in the simulation. The specific tasks that were tested in the simulation are 1. Testing adding a collision waypoint avoidance into the mission list. 2. Testing sending new mission commands to the vehicle. 3. Testing vehicle navigation to the avoidance waypoint. And 4. Testing resumption of the mission by the vehicle after avoidance. Here, we can see the results of the simulation. The black line represents the own ship trajectory, and the red line represents the intruder trajectory. The dashed lines indicate the headings of the two vehicles. Prior to point 1 and at point 2, predictions did indicate that a collision would occur, and appropriate collision avoidance maneuvers were undertaken, as seen at point 1 and at point 3. Following the maneuvers seen at point 3, the vehicle no longer predicted a collision and returned to the waypoint mission, as seen at point 4. The same tasks, tasks 1 to 4, were tested in the flight test. During the flight task, the operation is slightly different. The pilot manually took off the own ship, and once airborne, the vehicle was switched to autopilot mode. Here, it can be seen that the own ship heads to waypoint 1 as the vehicle is set to auto mode. Although it seems like the own ship collides with an intruder between waypoint 2 to waypoint 3, the trajectory overlap happens in different time frames. The own ship and intruder's current positions are marked as blue dots in their trajectories. It was expected that the avoidance waypoint would be triggered and an avoidance waypoint would be generated for the own ship to navigate to. However, the avoidance waypoint was not generated and caused the own ship to loiter at the point of the own ship's current position. After the collision was cleared, the own ship resumed its mission and returned home. As such, the tasks 1 and 4 were successfully completed, but the tasks 2 and 3 failed. The collision prediction algorithm and resumption of the mission worked as expected in flight, but the collision avoidance algorithm did not. The failure to generate a valid avoidance waypoint in the flight test is under investigation and will be reported on in the future. This is likely due to an issue with the implementation of the algorithm and its communication with the Pixoc autopilot during flight tests. In conclusion, the proposed algorithm presents a low-complexity algorithm for the collision detection and avoidance for a fixed-wing UAV equipped with an ADS-B transceiver or a custom ADS-B-like solution. The collision prediction method approximates the future position of the nearest intruder aircraft and the own ship to a high degree of precision, ensuring that any likely collisions are predicted. This makes it a viable solution for implementation into high traffic density airspaces, where the management of aircraft velocity and altitude is critical, and avoidance maneuvers must be generated rapidly in order to deal with the dynamic environment. In our simulations, our prediction algorithm is able to predict collisions as planned, and our avoidance algorithm generates appropriate avoidance waypoints. However, while during our flight test, our prediction algorithm is successful in predicting collisions, the airplane does not proceed to generate waypoints and loiters instead, suggesting an issue in the way our waypoints are given to the autopilot. For our future work, we aim to further refine our collision avoidance algorithm, such that our algorithm functions as it does during simulation. Furthermore, we will need to conduct more flight tests involving both the own ship and intruder vehicles to fully test the collision prediction and avoidance algorithms. In the future, we also aim to implement spline-based path generation for consecutive avoidance maneuvers, as well as improving our 3D avoidance capabilities using our energy function to optimize for desirable aircraft states. Finally, we also aim to eventually implement considerations for aircraft turn radius and time required to execute avoidance maneuvers. Thank you for your time. I would like to thank the NSF Research Experience for Undergraduate Program, the Lockheed Martin Corporation for their funding support project review, and UAV pilot Tristan Sherman of California State Polytechnic University, Pomona.